Welcome back again. This is Dr. Kofelt. We're ready to do chemical equations. This is exactly what we've been trying to get to. We're going to balance equations. We're going to determine what these equations tell us, because this is where we're describing the reaction, what's going on. And so once we can do this, we can predict all kinds of things. So a chemical reaction, as described in Dalton's theory, is a rearrangement, right? A rearrangement of atoms in a sample of matter. So we're not creating or destroying, but we're rearranging. And we could, examples we've seen before: rusting iron, exploding something catching on fire, all kinds of things. So we use a chemical equation to use chemical symbols to describe what's actually going to be occurring in that chemical reaction. So if you look at this chemical equation here, what it's telling me is that ammonia and hydrochloric acid are combining to produce ammonium chloride. So that arrow means to produce or reacting. Calcium carbonate, you know how to name these, produces calcium oxide and carbon monoxide. Okay, so that's how you read this chemical equation once you see it. It's also important that we tell you what physical state these things are in. And we use italicized letters in parentheses to do that. Gases are the letter G, and it's italicized, so you can kind of tell it's a little bit different. Solids are S. Liquids are L, and that's usually water, okay? And then there's another term, AQ, for aqueous or aqueous, depending on where you're from. Okay, and that tells us that it's something that's dissolved in water. Okay, so gas, liquid, solid, and then aqueous. So allotropes basically are the same element that are in different physical forms. Okay, for example, carbon has many forms. It can be graphite, which is in what we call lead pencils, which isn't really lead, it's carbon in the form of graphite. Or a diamond is also just carbon put together in a very strict, rigid arrangement. Okay, so if we were able to put enough heat and pressure and all that stuff, and we had oxygen available, we could produce carbon dioxide if we had carbon. Now, graphite's a whole lot easier to do than diamonds, let me tell you. But the allotropes are just the same element in different physical states. So when we have equations, we have to be able to balance them, because remember, we can't create or destroy matter, we can only rearrange it. And so the balanced chemical equation must have the same number and kind of elements on each side of that arrow. Okay, so here's our arrow. And so H2 means that we have one molecule that's got two hydrogens put together. O2 has two oxygens that are attached to each other, and water has an O and two H's, which are attached together. Okay, and so then that's the molecular formula. That's the Ball formula. Okay, and so when we put this in a reaction, in order to have the same number of hydrogens and oxygens, we have to balance it by adding coefficients. We can't change that because that's what this is, H2. If I change this number, okay, the subscript, that changes what the compound is. So I can only balance by using coefficients in front of the formulas. What we're going to see is that it's going to cause a little problem when we go back and forth, because if I put a 2 in front of H2O, it not only is going to give me more H's, but it's also going to give me more O's. So let me show you what I'm talking about. So you balance it. The book says it's trial and error. I really think it's not. I think that it is something, it's like taking an inventory, okay, and you change the coefficients as you go. And there's just a couple of rules that'll make this easier, okay? So make sure you don't change the subscripts. You only change the coefficients, which are the numbers in front of each one of those molecules. If you have a polyatomic, you don't bust it apart. You leave it together and you balance it as a ClO3 2-, okay? You don't count each, chlorine and oxygen and all that. Now, and again, I'm going to do one, and so you're going to see what I'm talking about a little bit better. If oxygen and hydrogen are in the equation, okay, you're going to do everything else except them, and then you're going to do the hydrogen and then the oxygen. And that's important because a lot of times oxygen will be in a reaction like as O2, okay, and so it's by itself, so you can kind of change it to whatever you need it to be. Count your atoms and your polyatomics carefully, and you track each number every time you change a coefficient. Now, this is showing you the combustion of butane. This is butane, which is a gas, and you must have oxygen if you're going to burn it or combust it, and it's going to produce carbon dioxide and water. Carbon dioxide is a gas, water is going to be a liquid. So when you start out, you take inventory. You've got 4 carbons on the left and only 1 carbon to the right of the arrow. You have 10 hydrogens on the left and 2 hydrogens on the right. You have 2 oxygens, okay, O2 is 2 oxygens, and you have 3 oxygens on the left. And if I have oxygens in more than one place, I usually do it like this because it helps me keep up with which one I'm changing. So the first thing I'm going to do is I've got carbon, hydrogen, and oxygen. So rule is I'm going to balance the things that aren't hydrogen and oxygen. So I'm going to balance the carbon first. So I have 4 on this side and I need 4 on that side. So in order to do that, I'm going to have to multiply carbon dioxide by 4. Now that does give me 4 carbons, but it's also going to change the number of oxygens, okay? I still only have 2 over here. Now I have 4 times 2 is 8, plus 1 is 9, okay? So now I have 2 on one side and 9 on the other. But don't panic, it's okay, because remember, we're going to do the oxygen last. So next, so now, check, my carbons are balanced. So now I'm going to go to my hydrogens, okay? I have 10 hydrogens over here from this, and I need 10 on the other side, which means I can, if I multiply, I've got H2, so if I multiply water by 5, that's 5 times 2, gives me 10 hydrogens, but I now have 5 more oxygens. So now I still only have 2 on the left side, and on the right side I have 13. I have 8 plus 5 is 13, okay? And again, I just keep up with that because it's just in my head, it's easier to do. Now, I have carbon balanced, hydrogen balanced, and oxygens are balanced if I put 13 halves times O2, okay, so that's 13 over 2 times 2, gives me 13 oxygens. So that balances those. What's my problem though? I can't have a fraction of oxygen. They have to be reacting in whole number ratios. So what am I going to do to get rid of that fraction? I'm going to multiply everything by 2. When I do that, that's going to give me 2 times 1 butanes, 2 times, that was 13 over 2 oxygens, which is now 13. I have 8, so 4 times 2 carbon dioxides, and 5 times 2, which is 10 waters. Now I go back and check it to make sure it's right, and indeed I have 8 carbons on each side. I have 20 hydrogens, and I have 16 plus 10 equals 26 oxygens on both sides. Alright, so it's balanced. These are the most complicated ones. If you have an oxygen in there that's a combustion, that one's going to be a little more complex than some of the others. I've got a couple of sample problems that I'm going to work for you to take you through this, okay? And then I'm going to give you practice as usual, and then of course I'm going to give you extra practice if you're in my class in Blackboard, okay? All right, so in this case, notice I'm going to show you something that'll make your life easier. Water is H2O, but it's also can be thought of as HOH. Why am I doing that? Because I have OHs on this side, and I can balance OHs if I have an OH on that side. So when I have water and I have a hydroxide on the left-hand side, then I'm going to consider that to be a hydroxide. Okay, so now I've got barium, I've got hydroxide, because I'm gonna just leave that like it's together, which it is, and I have 2 of those. All right, I have a hydrogen, and I have a polyatomic, which is ClO4 minus. Okay. And you don't have to worry about the minus and all that stuff because they're both going to be the same charge. We're just balancing the overall thing. All right, so on this side, I have 1 barium, I have 1 hydroxide, kind of do them in the same order so you don't get confused. Then I have 2 hydrogens I only have 1 hydrogen. So I have 1 hydrogen and 1 hydroxide. And then I have, for my ClO4, I have 2 of those on this side. Okay, so my bariums are okay for now, so I'm not going to worry about them. I've got hydroxides and I've got chlorates. All right, so you can pick whichever one you want because it's not an oxygen, it's a hydroxide. Okay, so I'm going to do, let's say, hydroxide first. Okay, so if I do hydroxide first, I've got 2 on the left side of the arrow, so I need 2 over here. What do I have to do to get 2 on the right hand side? I have to do 2 waters, okay, and then if I do 2 waters, that's going to give me 2 hydrogens, because remember I'm looking at this one, and 2 hydroxides. Okay, so now my hydroxides are balanced. but I have 1 hydrogen on this side and 2 on that side. You can go ahead and do the hydrogen, or let's look at the chlorate and follow those rules that we talked about first. I have 2 chlorates on this side and only 1 on the left-hand side. So I know I'm going to need 2 on this side. So that will then 2 times the chlorate gives me 2. And now 2 hydrogens gives me 2. And so now I've got 1 barium on both sides. I've got 2 hydroxides on both sides. I've got 2 hydrogens on both sides. And I have 2 chlorates on both sides. So I'm balanced and I am done. So it takes practice, but it's really not as hard as some people sometimes think. All right, now this one, we've already been going 15 minutes, but I wanted to do another combustion with you just so you see, okay? So on this side, I have, and I don't have any polyatomics this time, so my water is going to stay the same. So I've got CHO and CHO. I have 4 carbons. I have 8 hydrogens, and I have 4 oxygens, which is 2 plus 2. On this side, I have 1 carbon. I have 2 hydrogens, and I have 3 oxygens, which are 2 from the carbon dioxide plus 1 from the water molecule. All right, so if I follow my rules, I'm going to do carbons first. So I'm going to multiply CO2 by 4, so I can get 4 carbons on that side. So 4 times 1 is 4, so I have 4 carbons. But it also changed my oxygens. So 4 times 2 is 8. So I now have 8 plus 1 is 9. Okay. My carbons are balanced. So I have to balance my hydrogens. So I've got 8 on this side. I need 8 on the right. So what I have to multiply my water by 4 to get 8. So I now have 4 times 2 is 8 hydrogens. And I have 4 instead of 1 oxygens. So 8 plus 4, 8, 9, 10, 11, 12. I've got 12 on this side and 4 on this side, right? So what do I need to do in order to have 2 plus something to equal 12? I'm going to have to multiply, if I multiply this by 5, that gives me 10. But I've already got 2. So that would give me 2 plus 10 equals 12. And I've got 12 on this side. So now everything is balanced. So I didn't have to do the fraction thing this time. It worked out without it. So if you get this to an even number, a lot of times that'll happen. You just have to remember that you're only going to have to multiply this one by 5 because you already had 2 from the butane. Okay? I mean, sorry, not butane, but butyric acid. All right, makes sense? Cool beans. All right, so I've given you a practice. I actually gave you 2 practices. One you've got to write and balance the chemical equation. And you can do this because you know it's combustion. So you're going to add oxygen to it, right? And you're going to then, you know, your products from combustion are always CO2 and water. All right, combustion, that's always the case when you're burning a hydrocarbon. This one is going to be an acid and a base, and so write those formulas, and it tells you it's going to form water and sodium sulfate, and you can put that together because you know how to do it. All right, Good luck, and I'll see you again.